Good evening, everyone. I'm Urvi Mehta. I'm from Ramaya University of Applied Sciences, Bangalore, India. I'm pursuing my bachelor's in aerospace engineering. Today, I'm going to be talking about investigation of hypersonic boundary layer instability for a flat plate geometry, considering both sharp and blunt leading edge cases. This particular project was done under the supervision of my mentor at my university, Dr. Jayhar Sivasubramaniam. The reason that we selected a flat plate as the geometry was because since it's less complex, it will help us to dig deeper into the flow's physics and analyze the stability in a better way. This is the outline for the presentation. We would be starting with introduction of the linear stability theory to the factors affecting it. Later, we would move on to the methods and the softwares which are used, followed by the solver setup, and then we would focus on the results, that is contours, the profiles, and the eigenvalue spectrum. We would conclude the session with future work, a conclusion, and references. So about linear stability theory, as you can see, this is a diagram of a flat plate which shows the laminar region is being converted to turbulent flow. That is, the laminar flow is transitioning to turbulent flow. So there are two cases which we can see. When small perturbations are applied to the laminar flow field, these small perturbations that are disturbances, they can either amplify or they can dissipate and eventually fade away. If they were to amplify and continue to grow, it would transition and turn into turbulent flow. On the other hand, if the small perturbations were to dissipate and fade away, the flow would continue to be laminar in nature. There are four principles which are involved in the linear stability theory. The first one is equilibrium flow. The flow properties do not change with time. Eigenvalues and eigenfunctions are nothing but the parameters which help us to determine stability. Small perturbations are nothing but the disturbances which we are applying to the laminar flow field. And linearized equations are nothing but the non-linear equations. We are converting them to linear equations. So this is about linear stability theory. When we talk about hypersonic boundary layers, there are four instabilities that come to mind. We'll be only focusing on the first mode and the second mode instability. The Gotler instability and the crossflow instability involve curvature and 3D effects, which is out of the scope for this particular project. Thus, we only focus on the first mode and the second mode instability. The first mode instability basically has eigenvalues of the lowest value, and the second mode has the second lowest eigenvalues. From this plot that we see of frequency and local Reynolds number, we observe the first mode instability curve and the second mode instability curve. There are three cases, as you can see, 1, 2, and 3. So here in this case, we only observe the first mode instability. In the second case, we observe the first mode instability and then the second mode instability comes into the picture. But in the third case, we observe only the second mode instability. For our project, we'll observe the first mode instability and then the second mode instability comes into the picture. So the first mode instability disturbances continue to exist, on top of which the second mode instability comes into the picture. Here, the second most instability is considered to be the dominant one because it amplifies the mode. It's the most amplified mode when compared to the first mode. So the factors which affect the boundary layer transition are the free stream turbulence, the pressure gradient, Reynolds number, and Mach number, also the disturbances which are acting on it. Other than that, the geometry's roughness, temperature, and curvature also play a role in affecting the transition. The main objective is to perform the numerical simulation for the leading edge as well as the sharp edge radius, and to also focus on the flow physics and to study the stability parameters. Here I've considered around 5 cases, the sharp leading edge cases and 4 blunt leading edge cases with varying nose radius from 10 micrometer to 1000 micrometer. The methods and methodology. So here I have used about 4 softwares, Pointwise, SU2, Python and Fortran, and TechPlot. Pointwise is nothing but a meshing software that uses glyph as a scripting language. SU2, of course, we know it uses C++ and Python. I have used Python separately to find out the derivatives of the velocity profiles which are being extracted from the SU2 simulated data. And Fortran is nothing but for the LST software, which will help us to generate the eigenvalues using the Linux operating system. TechPlot is just to use the to plot the results obtained. So the solver setup for the SU2, I have used, since the flow is compressible, I have used Navier-Stokes density-based solver. The fluid model is ideal gas. Viscosity model is Sutherland viscosity model. For the convective flow numerical method, I have used AUSM plus UP. These are nothing but the flow conditions, that is Mach number of 5.35 and free steam temperature of 64.3163 Kelvin. There's a very similar experiment conducted by IISc from the Aerospace Engineering Department. They are focusing on a flat plate geometry, very similar to the case that I have taken. And they have their own hypersonic shock tunnels and they are conducting the experiment. The experiment is being conducted by Professor Gopalan. Yeah. So the reason that I've selected the flow numerical method as AUSM for its robustness and accurateness, and the upper pressure bound, that is UP, basically helps us for getting a pressure field that's physically realistic. So after the flow conditions, I'll move on to the mesh part. So this is the mesh for the sharp leading edge, and these are the boundary conditions. This is the inlet, this is outlet, this is the wall, and this is the symmetry. So this is for sharp leading edge, and for blunt leading edge, this is the geometry that I've chosen. This is the magnified view of the generated mesh. It consists of about 200,000 grid points. The reason that we are focusing for this particular mesh is because we are only extracting the profiles perpendicular to the flat plate on top of it. So the bottom part does not really matter much. We're only focusing on the top layer. So this is nothing but the inlet. These two edges are the outlet, and this is the wall. So now coming to the results part, I have mainly chosen Mach number, density, and temperature as the contours. So here I have chosen three cases specifically. This is the sharp leading edge case with a radius of 0 meter, blunt leading edge case with a radius of 16 minus 5 meter, and here the nose radius is about 1e minus 3 meter. So this is the most blunt leading edge, this is moderate, and this is the sharpest leading edge. So there is a trend that we observe. As we increase the bluntness, we observe that the shock standoff distance also increases. Not only that, but the boundary layer thickness also increases. So that you can see from the y-axis scale, the boundary layer region also increases. For the Mach number contour, we observe that downstream of the shock, the velocity, it decreases. Therefore, with increase in bluntness, the downstream of the shock, the velocity, it continues to decrease. Coming to the density contour, as we know, we have chosen the flow to be compressible. So the downstream of the, aside from the regular trends that we observe of the shock standoff distance and the boundary layer thickness, we also observe that there is a strong pressure gradient that comes into the picture. And due to that, there is a significant increase in drag downstream of the shock. So that's what you observe in this particular contours. And moving on to the temperature contours, here downstream of the shock, there is a significant increase in the temperature as well. Now we know that temperature and entropy are actually related to one another. So entropy layer naturally comes into the picture. Entropy layer is nothing but it's a layer which deals with all the vertices. So there is a point known as entropy swallowing point. It is that point where the boundary layer, it swallows the entropy layer, and then the transition occurs. The distance between the nose radius and that entropy swallowing point is said to be the entropy swallowing length. So as we increase the bluntness, we also observe that the entropy swallowing length, it increases. And since the entropy swallowing length increases, the point at which the boundary layer takes in the entropy layer also increases. Thus, it delays the transition. Therefore, with increase in bluntness, we are delaying the transition. And of course, the normal trends that we observe, that is the boundary layer region, the thickness, it increases. Also, the shock standoff distance also increases. Another thing that we observe is that when we increase the bluntness, we also observe that the shock wave strength, it also increases. Thus, that explains the rapid spike in temperature and drag. So coming to the velocity profiles, so the velocities were plotted. So you consider a flat plate and you extract the velocity profiles perpendicular to that flat plate. And this is then plotted with respect to the literature value. As you can see, the SU2 simulated data and the literature data, they're almost coinciding, thus indicating its accuracy. Here, as you can see, the curve is slightly different. This indicates that the boundary layer thickness is increasing with increase in the X location. This was taken at 0.1 meter and this was taken at 0.3 meter. So boundary layer thickness is continuing to increase along the X direction. Same plots can be observed for the temperature profile for 0.1 and 0.3 meter. Again, you can see how accurate the simulation data is with the literature data. Now I'm comparing the effect of the leading edges. So this is nothing but the magnified view of this particular plot. As you can see, the black line, which indicates the 6e minus 5 meter, which is the least blunt leading edge, and the blue is the maximum blunt leading edge. So we observe that with increase in the bluntness, we observe that the boundary layer thickness also increases and the velocity decreases for each location. Same thing can be observed for the temperature profile, how this is the most least blunt leading edge and this is the most blunt leading edge, and how the boundary layer thickness is being affected by it. This is for the 0.3 location, earlier was for 0.1 location. Yes, so here I'm comparing the sharp and the blunt leading edge cases, how they vary with one another. As you can see, the sharp leading edge has a comparatively lower value of boundary layer thickness when compared to the blunt leading edge. Coming to eigenvalue spectrum, so this is nothing but when the velocity profiles which are extracted perpendicular to the flat plate, it is being sent into the Python code, which finds out the derivatives of those velocity profiles, and it acts as an input file for the linear stability solver. Linear stability solver, it generates the eigenvalues. And then we plot the eigenvalue spectrum. Eigenvalue spectrum, it basically represents the streamwise wave number of the disturbances and perturbations in the boundary layer. We know that eigenvalues are complex numbers, that is, they have imaginary part and real part. So the plot between the imaginary and the real part as the y and x axis is what gives us the eigenvalue spectrum. Based on this, we can actually figure out if there are any unstable modes present or not. There can be continuous spectra or there can be discrete spectra. Here for the sharp leading edge case, I have chosen case A and case B. These are the locations at which I've extracted the profiles, and these are nothing but the local Reynolds number. So from figure 33, you can see that there is no unstable discrete mode. Right? There is no negative alpha value or positive for alpha r. These are just three branches that you see. But here you can see a discrete mode with an alpha I value of minus 0.004 and a positive alpha R of approximately 0.3. This indicates that the negative alpha I value indicates that it is highly oscillating in nature, and the positive alpha R value indicates that it continues to grow. It continues to amplify, thus terming it as unstable point. So this is an unstable discrete mode for sharp leading edge case. But when you consider the blunt leading edge case, Here the frequency chosen is comparatively less, around 50k hertz. And here again, there are no unstable discrete mode, but here you can see there is an unstable discrete mode with an alpha I value of 5 into 10 raised to minus 4 negative value, and the alpha R is approximately equal to 0.1. So here the alpha I value is comparatively less negative, and this particular plot was obtained for a comparatively lower frequency band. Coming to these three branches, so the horizontal branches that you see, these are known as the acoustic modes, and this is said to be the entropy and the vortices mode. So the reason that these are connected is because of fast moving acoustic modes, and the reason that this is not connected is because of slow moving acoustic modes. So another thing that we can actually obtain from these eigenvalue spectrum is that with increase in bluntness, we also observe that the alpha I value, it becomes less negative. The amplification factor decreases. Also, the frequency band also decreases. That is when we increase the bluntness. If the eigenvalues spectrum is plotted for more locations and for appropriate frequencies calculated using the formulas, eventually we can obtain a plot very similar to the one that I showed in the second slide. That is the plot between the frequency and the local Reynolds number, which would result in a banana shaped like curve, which would tell us about the unstable points and the stable points. Any points which would come under the banana shaped curve would be unstable, and any points outside of it would be considered as stable poles. And this is said to be the neutral stability diagram. It will help us realize that which mode is the dominant mode and why it is the way it is. Another study that can be done is focusing on the nonlinear regime. And we can also introduce 3D perturbations and not just 2D perturbations to the boundary layer. So to conclude, I have focused on the flow features and the trends that we see when we increase the bluntness. I've also explained how we can see that the transition location varies downstream when we increase the bluntness. We have also seen how the stability characteristics affects the bluntness. SU2 proved to be a right choice of software for this because we were able to extract the boundary layer profiles, which almost coincided with the literature data, thus proving its accuracy. Not only that, my experience with SU2 was I found it to be very user-friendly. There were many test cases available online and also the master script file, which gave me an idea on how to run the simulation and what should the script file look like according to our needs. It has a wide range of applications as well. So this was how I used SU2 to conduct this research project. It's still in progress. It's at the mid stage, I would say. There's still a lot to do, but yes, this is how I use the software. These are the references that I've used. Thank you so much for listening. If there are any questions, I would be happy to answer them.
Yes. Why for predicting transition flow, why did you have to use the solver here and not the turbulent form?
Sorry, why you have to use the
Yes. Why did you have to use the solver and not some sort of LES or here?
The question is about the choice of the nanotube solver and not a choice of turbulence modeling such as LES. Am I right?
Yes, so that's a very good question. The reason I chose that is because linear stability theory, it mainly relies on the theory that the flow is initially laminar and then it transitions. So that I've not introduced any turbulence model because of that particular reason. Initial flow is laminar and then it transitions.
Is it okay? Okay, let's thank our speaker.
Yeah.